block. If we slowly increase the inclination of the surface on which the block is placed, there comes a point where the block starts sliding. At this point, the weight of the block, which is equal to mg, acts vertically downwards. If theta is the inclination of the surface with the horizontal, then mg sin theta acts down the plane and the static friction acts up the plane as shown. Thus, mg sin theta is equal to Fs. The normal reaction on the block acts perpendicular to the surface as shown, and it is equal to mg cos theta. As per the laws of friction, if μs is the coefficient of static friction, then Fs is the product of μs and n, which is equal to μs mg cos theta. As the value of theta increases from minimum, the value of mg sin theta and as well as the value of Fs2 increases till the value of theta is equal to a maximum theta max. At this maximum value of theta, the block tends to move down the plane and experiences impending motion. Then the friction is limiting friction. In this case, mg sin theta max is equal to Fs max, implies mg sin theta max is equal to μs mg cos theta max, which gives tan theta max equal to μs on simplification. Now let us look at a rolling friction. When cylindrical or spherical shaped bodies roll without slipping on a cylindrical or flat surface, the frictional force is minimal. A ball or roller bearing fall in this category. To reduce the friction further, grease or lubricating oil is introduced between the surfaces. Air is used as a lubricant in high precision and high speed equipment. Friction is desirable or undesirable depending on the situation in which it occurs. Friction between the moving parts of a machine is undesirable. We try to reduce friction by using lubrication. Friction is desirable when it occurs between the tires and the road's surface. Because of this friction, the automobile is able to move forward or stop when brakes are applied. We are able to walk only because of the friction between our feet and the ground. We would fall if we try to walk on a slippery surface. Have you ever wondered why a velodrome track is curved? Or, on a rainy day, while driving a car at high speed, what happens if you take a sharp turn on a flat road? You will get the answers to these questions in this module. You have earlier studied the acceleration of a body moving in a circle at uniform speed. Here, Fc, the force directed towards the center of the circular path, is the centripetal force. Centripetal force, Fc, is equal to mv square by r. A simple example of centripetal force is that of a stone tied to a string and rotated in a circle in a horizontal plane. The tension, T, in the string provides the required centripetal force. This tension in the string is due to the pull exerted on the string by the person, which prevents the stone from flying away. Similarly, a car moving along a circular path at uniform speed also requires a centripetal force to keep it moving along the desired circular path. In this module, we will analyze the forces acting on the car during this motion. Let us consider a car moving on a level, curved road. There are three forces acting on the car, namely, weight of the car, mg, normal reaction, N, and frictional force, F. As there is no motion in the vertical direction, the net force in the vertical direction is 0. We can say that normal reaction is equal to the weight of the car, mg. Let us call this equation 1. The static frictional force between the tires and the surface of the road opposes the impending motion of the car in the lateral direction away from the center of the circle. This frictional force, F, is less than or equal to the product of the coefficient of the static friction, mu s, and normal reaction, N. Let us call this equation 2. Substituting equation 1 in equation 2, we get F less than or equal to mu smg. Let us call this equation 3. The centrifugal force, Fc, is equal to the frictional force F. Let this be equation 4. However, Fc is equal to mv square by r. Where m is the mass of the car, v is the velocity of the car, and r is the radius of curvature. Let us call this equation 5. Substituting equations 3 and 5 in equation 4 and simplifying, we get maximum velocity, Vmax, as the whole root of mu srg. That was about a car moving on a level, curved road. Now let us look at a car moving on a banked road. Let us analyze the forces acting on the car one by one. The weight of the car, mg, acts vertically downward. The normal reaction, N, acts upward perpendicular to the road's surface. The impending motion of the car in the lateral direction is away from the center of curvature in the lateral direction. The frictional force, F, acts opposite to this direction, that is, down the lateral slope. We can resolve the normal reaction, N, into its horizontal component, N sin theta, and vertical component, N cos theta. Similarly, the frictional force, F, can be resolved into its horizontal component, F cos theta, and vertical component, F sin theta. We can represent all the components of all the forces at a point C. Along with the weight mg as shown. As there is no motion of the car in the vertical direction, the net force acting along y direction is equal to 0. Or N cos theta minus mg minus F sin theta is equal to 0. This implies N cos theta is equal to mg plus F sin theta. Let us call this equation 1. We know that frictional force F is the product of mu S and N. Let this be equation 2. Substituting equation 2 in equation 1, we get equation 3 as n cos theta equals mg plus mu S n sin theta. The car experiences acceleration acting towards the center of curvature. This is the centripetal acceleration, and the force required for this acceleration is the centripetal force Fc. Centripetal force Fc is equal to the net force acting along x direction. This gives us equation 4 as n sin theta plus f cos theta equals Fc. Substituting equation 2 in equation 4 and solving, we get equation 5 as n sin theta plus mu s n cos theta equals Fc. But Fc is equal to mv squared divided by r. Substituting this in equation 5, we get equation 6 as shown. From equation 3, n is equal to mg divided by cos theta minus mu s sin theta. Let us call this equation 7. Substituting equation 7 in equation 6 and solving, we get the maximum velocity, Vmax, as shown. Now, dividing all the terms on the right-hand side with cos theta, we get equation 8 as shown. If the frictional force is negligible, the maximum velocity, Vmax, is equal to the whole root of rg tan theta. There is a systematic way to tackle problems in mechanics. Draw a free body diagram. Choose convenient coordinate system. Consider all the forces acting on the body. Resolve the forces in the chosen coordinate system. Apply Newton's laws of motion and solve all the equations to find the unknown variables. Let's take a look at each of the steps involved. To draw a free body diagram, we need to draw a schematic diagram showing all the bodies in an environment along with their links and supports. Then, we consider a convenient part of this diagram, relevant to the problem at hand, as a system. Then, we draw a detailed diagram of this system along with the external forces acting on it. This diagram is known as a free body diagram. This completes step 1 of the solution. In a free body diagram, we do not consider the forces applied by the system on the environment. Next, we choose a convenient coordinate system to resolve the forces involved. Coordinates should be chosen keeping in mind the probable direction of motion of the body. This makes the solution easier. Then, we add details about all the known and given forces on the system, indicating their respective magnitude and direction. Then we resolve all these forces along the chosen coordinate system. Finally, we can take the help of Newton's laws of motion to determine the magnitude and direction of unknown forces. If the problem at hand requires an analysis of multiple systems in an environment, we follow the same procedure for each individual system. To understand these steps, let us take a problem and solve it systematically. Bodies A and B of mass 10 kilograms and 30 kilograms respectively are connected by a rope of negligible mass passing over a frictionless pulley. The coefficient of friction between the masses and the inclined planes is 0.30. Determine acceleration of the system. Tension in the rope. Velocity of the system at the end of 4 seconds starting from rest. First, we draw the free body diagram. Here, as the two bodies are connected by a rope, we split the problem into two parts and tackle them independently. As the mass of B is greater than the mass of A, and the inclination of the plane on which B is resting is greater than the inclination of the plane on which A is resting, B is likely to go down and A is likely to go up the plane. Next, we choose a convenient coordinate system, XY, such that X is parallel to the inclined plane and Y is perpendicular to it. We choose X parallel to the plane, as body A is likely to move along the plane. This will make the application of Newton's laws of motion easier. Then, we denote the forces on body A, which are its weight, mg, or 98.1 newtons, and tension in the rope, T, which is unknown. Next, we resolve the weight of body A along x and y coordinates. The x component is equal to mg sine theta, which is equal to 49.05 newtons. Similarly, the y component is equal to mg cos theta, which is equal to 84.96 newtons. As there is no motion of A in the y direction, we can say the net force along y direction is 0. Summing up the forces acting along y direction and solving this net force equation, we get the normal reaction N as 84.96 newtons. Let us call this equation 1. As A is moving up the plane, the frictional force F acts downward. F is equal to the product of the coefficient of friction, mu, and normal reaction, N. Substituting the value of N from equation 1, we get the frictional force F as 25.49 newtons. Let this be equation 2. As A is moving up the plane, we take the inclined plane's upward direction as positive. Using Newton's second law of motion, the net force along x direction is the product of the mass of the body A and its acceleration. Substituting values and solving, we get equation 3 as T minus 74.54 is equal to 10 times the acceleration of body A. Now consider the other part, that is, body B, and draw a free body diagram indicating the forces and a convenient coordinate system. The weight of the body B acts vertically downwards. This force can be resolved into its x and y components as mg cos theta and mg sin theta. Mg cos theta is equal to 147.15 newtons and mg sin theta is equal to 254.87 newtons. As there is no motion of B in the y direction, we can say the net force along y direction is 0. Summing up the forces along y direction and solving, we get the normal reaction N as 147.15 Newton. Let's call this equation 4. As the body B is moving down the plane, the frictional force F acts upward. F is equal to the product of the coefficient of friction, mu, and normal reaction, N. Substituting the value of N from equation 4, we get the frictional force F as 44.15 newtons. As the body B is moving down the plane, we take the inclined plane's downward direction as positive. Applying Newton's second law of motion, the net force along x direction is the product of the mass of the body B and its acceleration. Substituting values and solving, we get equation 5 as 210.65 minus t is equal to 30 times the acceleration of B. Since A and B are connected to each other with a rope, the magnitude of their acceleration is equal. Substituting equation 6 in equations 3 and 5, we get t minus 74.54 equals 10a as equation 7. And 210.65 minus t equals 30a as equation 8. Equations 7 and 8 are simultaneous equations with two unknowns, which are t and a. Adding these equations and solving, we get acceleration as 3.4 meters per second squared. Substituting the value of A in equation 7 and simplifying, we get the tension in the rope T as 108.54 newtons. Now, we need to find the velocity at the end of 4 seconds. Given that the initial velocity of the system, v0, is equal to 0, acceleration of the system, A, is 3.4 meters per second squared, and time t is 4 seconds. We can use the equation of motion. V is equal to v0 plus at to determine the velocity at the end of 4 seconds. Substituting the values and simplifying, we get the final velocity, v, as 13.6 meters per second. Another way to solve this problem is that we can combine the two bodies A and B along with the rope into a system. Tensions T acting on body A and B now become internal forces and hence cancel out each other and will not be taken into consideration while writing the net force equation. The net force of the system along x direction is equal to the product of the total mass of the system and its acceleration. Substituting the values and solving, we get the acceleration A as 3.4 meters per second squared. The disadvantage of this method is that the tension in the rope T cannot be found directly. To find T, we have to write the net force equation for A or B, where we substitute the value of acceleration just obtained. That is, 3.4 meters per second squared. Let's consider the net force on body A along x direction, which is equal to the product of the mass of body A and its acceleration. Substituting the values and solving, we get the tension in the rope T as 108.54 newtons.